Okay, welcome back to Real Analysis. We are going to continue our work in Chapter 4 in Section 4.3, introducing two fundamental notions called open and closed subsets of the real numbers. So we'll start with one of our two main definitions, that is when a set is closed. So if you take a subset of the real numbers, we're going to call it closed if it contains all of its accumulation points. So if every accumulation point of E belongs to the set E, then we'll call the set E closed. If we give some notation, maybe I'll denote by E prime those real numbers that are accumulation points of E, then I'm saying E is closed if E prime is contained in E. Every accumulation point of E is actually an element of E. Let's look at some examples. The empty set is closed. The empty set doesn't have any accumulation points at all. No point in the real numbers can be an accumulation point of the empty set. So vacuously, all the accumulation points of the empty set belong to the empty set. Vacuously. Likewise, every point in R is an accumulation point, and certainly every point in R belongs to R, so R is also closed. And so we have two examples of closed sets. Let's look at some more here. The open interval from A to B is not closed. That's kind of a good thing. The open interval from A to B is not closed. Well, because one of its endpoints, say A, it's an accumulation point of the open interval, but it doesn't belong to it. So the open interval from A to B is missing one of its accumulation points, namely A. It's also missing B. B is another accumulation point of that set that's not in the set. So it's not a closed set. The terminology would be weird if example 3 didn't hold. The closed interval from A to B is closed. Okay, every point, the set of accumulation points of that closed interval we saw in the last lecture is that closed interval. So the closed interval from A to B is a closed set in our new terminology. The set of natural numbers is a closed set. Yeah, it doesn't have any accumulation points at all. So once again, every accumulation point of n belongs to n vacuously because n doesn't have any accumulation points. Its set of accumulation points is empty, right? So it's a closed set. The rational number is not a closed set. For example, any irrational number is an accumulation point of the rationals, but it doesn't belong to the rationals. Our set, the reciprocals of the natural numbers is not a closed set. Yeah, 0 is an accumulation point. Of E, but it doesn't belong to E. So E, if a set is missing so much as one of its accumulation points, it's not a closed set. Cool. Given a set, there's kind of an operation you can perform on it to create a closed set that contains it. It's called its closure. Sorry about that. So if you give me any set of real numbers, once again, the author is going to use the same notation I introduced. E prime is the set of all accumulation points. Then the closure of E is the set denoted by E bar. It's E together with its accumulation points. All right. So you just gather up all the accumulation points of E and you throw them in together with the points of E. You call that set the closure. I'm going to leave it as an exercise to you to show that the closure of a set E is in fact a closed set. All right. But just to give you some sort of examples of that, the closure of an open interval from A to B is the closed interval from A to B. You're probably not surprised the closure of the natural numbers is the natural numbers. And here I have a typo. I don't mean the closure of the rationals is the rationals. If you take the closure of the rationals, you have to take the rationals together with all of its accumulation points. That is together with all the rationals and the irrationals. So you get the real numbers. The closure of the rational numbers is the real numbers. So notice in all three examples that the closures there are closed sets. Okay, it's not an accident. You're going to think about that in one of your homework problems. Okay, moving along, the second of our two main definitions. What do we mean by a set being open? So a subset of the real numbers E is called open if every point of E is interior. So if you give me a point in E, that point is an interior point. Vacuously, the empty set is open. Every point of E is interior because there are no points in E if E is empty. Likewise, every point in the real numbers is interior to the real numbers. So the empty set and the real numbers are open. They're also closed. Those are in the real numbers, in the situation that we're studying these things, those are the only sets that are both open and closed. Right? So it can happen. Sometimes people, yeah, I'll just leave it at that. That the empty set and the real numbers are both open and closed. You can check every point interior. Every point of the open interval is interior to it. So that's an open set. Okay, every point in the open interval from A to B is interior. It was one of our first examples of an interior point. So it's an open set. The closed interval is not an open set because, for example, one of its endpoints, I picked A, it's in the interval, but it's not interior. I'm just stating these things. All of these comments I'm making about things being interior and ice and accumulation points, we talked about them in the previous lecture. So here I'm just sort of using them to illustrate these new notions. The natural numbers is not open. Natural numbers has no interior points. No point in the natural numbers is an interior point. So in particular, yeah, it doesn't have any interior points, so it's not an open set. Q is not open. No element of Q is inside of an interval that's completely contained in Q. No element of Q is interior to Q, right? So no element of Q is an interior point, so it's not an open set. Our set E, the reciprocal of the natural numbers, it's not a closed set. It's missing its accumulation point. We just said it. 0 is not in there, so it's not closed. It's not open either. Every point in there is isolated, so that it doesn't have any interior points. Okay, so there are points in E that aren't interior points, so it's not an open set. Kind of analog to the closure operator above is this kind of interior operator. If you give me any set of real numbers, then by int of E, or the interior of E, I mean the set of all interior points. So it's called the interior of the set. It's kind of its inside. It's the points in the set E that are interior to it. So just to give you some examples, the interior of the open interval is the open interval. Every point is interior. The interior of the closed interval is the open interval. Right? So it's not an accident here that the interior of these sets is open. I'm going to leave that as an exercise to think about. The interior of the natural numbers is empty. There are no interior points in N. There are no interior points in Q. So those sets have empty interiors. Also open sets. The interior of N is open. It's empty. Nice. Okay. Now we're going to get ready to state and then prove the main theorem of this section. It's going to be kind of a valuable tool for us in the future. It states that any open subset in the real numbers is a union of open intervals. So in some sense, open intervals build all open sets. And in fact, a slightly stronger statement that any open subset is a finite or countable union of disjoint open intervals. So a finite number of them or a countable number of open intervals, no two of which intersect. So that's what we're going to prove. It's this kind of structure theorem for the kinds of things that can be open subsets of the real line. They have to be just disjoint unions of open intervals, finitely many of them, or worst case, countably many of them. This proof is going to use the fact that the set of Q is countable. That is, that we can so-called enumerate or list the elements of Q, first rational number, second rational number, and so on. We kind of skipped over the countability section in chapter 2, so we didn't prove that. We'll return to it and talk about such things in 4.6. But for right now, for the purposes of this proof, I'm just going to make the assumption that I can enumerate the rational numbers. I can put them in an ordered list and talk about the first rational number, the second rational number, and so on. Okay. So Here is the statement of the theorem. If you take any non-empty open subset of the real numbers, it's called G, then there has to be some unique. I'm going to leave the uniqueness part out of this lecture. We can talk about it in class. There has to be some sequence. Maybe it's finite or maybe it's infinite, but if it's infinite, it's countable, of disjoint open intervals. So say some first one, some second one, some third one, nth one. If it's finite, that would stop for some n. They're going to be called the component intervals of G, and G is their union. So this non-empty open subset of real numbers can be written as a finite or countably infinite union of disjoint open intervals. All right, so let me try to walk you through the argument here. Here I've drawn kind of a picture of a G just to help us visualize some of the constructions. Okay, so let's take our non-empty open subset and pick an X in it. Pick an X in this set G. So G here, I've drawn it kind of as these purple blobs, and you can see I've picked an X down there. And once I pick that X, I define two sets. One of them, A sub X, are those real numbers A such that the kind of half open interval, open at A, closed at X, completely belongs to G. So I'm showing you an A down here in A sub X. Yeah, that half open interval from A to X completely belongs to the set G. So A sub X is the set of all such A's. All right. And then I'm also going to define B sub X. It's those B's that, again, the half open interval from X to B completely belongs to G. So I'm showing you a B down here that's in B sub X. So A sub X is the set of all such A's. B sub X is the set of all such B's. Okay, G is an open set, right? So there has to be some interval containing X that's contained in G. That's what it means to be open. Because X belongs to G, it's an interior point, and an interior point is contained in an open interval that's contained in G, right? So neither one of these sets is going to be empty. There's at least something in A sub X, there's at least something in B sub X, because there has to be some open interval around X that stays in G. Cool. Okay, so continuing along here. I don't know if A sub X is bounded below or not. But if it is, if A sub X is bounded below, I'm going to let little a sub X be its infimum. If capital A sub X is not bounded below, I just let little a sub X equal negative infinity. Likewise, if capital B sub X is bounded above, little b is its supremum. If it's not, little b is infinity. All right? And now a kind of important part of the proof here, that in either case, bounded or not, A sub X and B sub X don't belong to G. Okay, I didn't write it out here, but I'm going to try to convince you of that. So let me just kind of do it with a laser pointer. Why can't A sub X belong to G? Here I've kind of indicated where A sub X would be in my picture here. It looks like A sub X is bounded, but capital A sub X is bounded below. So this would be the sort of infimum of that set capital A sub X. And if that element A sub X belonged to G, well, G is an open set. So there would be some open interval containing A sub X that would be completely contained in G. And that open interval would have elements in it that were strictly less than A sub X, right? So I would have an element in this set G that's strictly less than A sub X. So the open interval, half open interval from that element to X would belong to G. So the endpoint of that open interval, maybe I could call it A prime temporarily here, that endpoint would be an element of capital A sub X that's less than the infimum of capital A sub X. And there is no such element. So that's why little a sub X can't belong to G. And likewise, little b sub X can't belong to G. That's in the bounded case. In the unbounded case, it's easier. Negative infinity doesn't belong to G because negative infinity is not a number. Okay, so neither one of those things in either case belong to G. Nice. Okay, let's call I sub X the open interval from A sub X to B sub X. Okay, so it's an open interval containing X. It's going to be our candidate for a component interval. So I got to prove some stuff about this the I sub x. So first of all, I claim that it's contained in G. Okay, going to do a pick a point proof here. Pick an element of I sub x. Look at some cases. Maybe my element y is less than x. All right. So y belongs to I sub x, so it's bigger than the endpoint. Remember, I sub x, maybe it's easier if I just write it here. I sub x is the open interval from a sub x to b sub x. So if y is in there, it's bigger than a sub x, right? So it's bigger than the infimum. Well, if you're bigger than the infimum of a set, there has to be some element of that set that's less than you, because you cannot be a lower bound. If you're bigger than the infimum, you're not a lower bound. So I have some a prime and a sub x that's less than y, okay? So therefore, y by definition belongs to it's bigger than a prime, it's written here, but y is less than x, so it's in the interval from a prime to x. But if a prime belongs to capital A sub x, that entire interval is in G by definition. So therefore, y is in G. So there's one case. If y is less than or equal to is strictly less than x, then y belongs to G. That's what I want. But I have to try the other case. If y is bigger than x, then by the same token, y is less than b sub x because it's in I sub x. And if you're less than b sub x, then you are not an upper bound, right? B sub x is the sup. So if you're not an upper bound, there has to be some element in that set that's less than you, or sorry, that's bigger than you. You're not an upper bound, there has to be some element in that set that's bigger than you. So therefore, y is in the half open interval from x to b prime by kind of a symmetric reasoning. And again, that's a subset of G because b prime is in capital B sub x. All right, so in either case, y being an element of I sub x means that y is in G. All right, I suppose I left out the case if y equals x, well, then it's trivially in G. So there we go. So that establishes the claim. Cool. So what did we just do? We just showed that every one of these I sub x's is a subset of G, so their union is a subset of G. But given an x, we said, well, there's an I sub x that contains x, and we just proved that I sub x is an element of G, so, or a subset of G. So G is contained in some I sub x. It's contained in that union. All right. So that union over all the x's and g's of these I sub x's is equal to G. So we're kind of half done in some sense. We've written G as a union of these open intervals, but now we got to kind of trim it down. We have to get it down to the countable or finite part. Okay, so moving on here. Second claim. Oh, and then by the way, trim it down to the finite part. And also, two of these things that aren't the same have to be disjoint. Okay, so that's what we're going to work on now. So let's suppose we take 2 points in G. They're different. X and Y are in G and they're different. And I'm going to claim that either I sub X is I sub Y or they're completely disjoint. And I'm going to prove that kind of logically by saying if they're not disjoint, then they're equal. All right, so let's suppose they're not disjoint. Suppose some element Z is in both of those things. Well, so first of all, Z is in I sub X, so it's between its endpoints. But Z is also in I sub Y, so it's between those endpoints. So now let me just kind of laser point so you can see here. So Z is at least A sub X, but it's no more than B sub Y, so it lives between A sub X and B sub Y. Good. Likewise, stop the video and figure it out, fill in the details. Z lives between A sub Y and B sub X. All right. So now, if you take A sub Y and A sub X, the left endpoints of these intervals, these component intervals, if they're not equal, well, either A sub X is less than Y or vice versa. Okay, well, if A sub X is less than Y, we'll just check out the cases one at a time. If A sub X is less than Y, then that would mean that AY belongs to IX. Why is that? Well, I'm saying that AY is at least A sub X right here. And then where did I write it? AY is certainly less than BY. I just lost it. Let me try it again. If a sub x is less than a sub y, I want to get that a sub y is less than b sub x. Ah, here it is. Sorry, I couldn't find it. A sub y is less than z, which is less than b sub x. So a sub y is less than b sub x, so it's in the interval ix. Good. Sorry about that. It's too late to stop this long video and try to edit it. All right. But wait a minute, a sub y belongs to I sub x, which is a subset of G. That means a sub y belongs to G, but we said above a sub y doesn't belong to G. So that's a contradiction, right? So it cannot be the case that a sub x is less than a sub y. So what about the other way? What if a sub x is bigger than a sub y? Okay, well then a sub x is bigger than the left endpoint of I sub y somewhere. I just have to search for it. I want to find a sub x is less than b sub y. Where is it? Aha, it's here. A sub x is less than z is less than b sub y. So that would put a sub x in the interval I sub y, which is in G. That's another contradiction. All right. So those two inequalities left to contradictions. So it must be the case that a sub x is equal to a sub y. They have to be the same. One of them can't be less than the other or vice versa. Stop the video and soak it in. And if you want to kind of test yourself, see if you can walk through the details in a similar way, you can prove that b sub x is b sub y. So what we've shown is that if the intersection of those two intervals isn't empty, they're equal. And that's claim 2. Nice. All right. So now it remains to show that we can do this with a countable or finite number of intervals. So here's where we're going to use this enumeration. Let's enumerate the rationals. Line them up, first rational, second rational, and so on. So take an enumeration of them. We've proved that the rationals are dense. So if you give me an x, the open interval I sub x has to contain a rational number. In fact, it has to contain infinitely many rational numbers. Each one of those rational numbers is indexed. There's a first one, a second one, and so on. So of all the rational numbers that are in I sub x, I can pick one. I'm going to call it r sub n of x because the index depends on x. And then n of x is the smallest. So I'm using the Well-Oring principle of the subset of the natural numbers of such that r sub that natural number belongs to I sub x. It's non-empty. There has to be a smallest one. So pick it. Right? So I'm choosing r sub n of x. It's a rational number, and it's in that interval. So those two intervals are equal. Right? That's what we just proved, that they're either equal or disjoint. But r sub n of x is in I sub x, so they're equal. Okay, and n of x is the smallest index where that's true. The smallest index n with I sub r of n of x equals I sub x. So what did that give us a way to do? That gives me a way to associate to distinct intervals I sub x a subset of the natural numbers, right? So when I give an I sub x, it picks off this special rational number, the smallest one. So I get an association or a function from these intervals I sub x into a subset of the rational numbers. So the collection of distinct intervals is, well, countable if that function has infinitely many elements in its range, and it's finite if it only has finitely many elements in its range. So when I've written this thing as a union of I sub x's, I either do it with a countable number and they're all disjoint, or a finite number and they're all disjoint. Okay, that was a lot to soak in. We'll talk about it in class, but I hope this is useful for you.